Hi, today I'll be presenting our work, PLATO, Predicting Latent Affordances through Object-Centric Play. In this work, our goal is to learn generalizable multitask policies from human demonstration data in an offline fashion. Typically, we learn multitask policies from different task demonstrations. For example, we might collect a data set with pushing right, pushing left, and lifting onto a platform. It's expensive to design and collect demonstration data, since tasks must be predefined by the designer with clear start and goal states, and require manual resetting of the environment between demos. Furthermore, policies trained offline to imitate these demonstrations often struggle to generalize online due to limited state action data coverage. Instead, we learn from human play data, a rich source of data consisting of unstructured and undirected demonstrations. An example of play is shown on the left. It is cheap to collect since no directions or resets are required, and it can cover a broad distribution of states, actions, and goals. Play also consists of significant prior knowledge about what goals and behaviors are possible in the scene. However, goals and task boundaries are not given. In this work, our goal is to utilize play to learn a single goal condition imitation policy for complex, varying length tasks. So in this work, we propose learning varying horizon tasks by viewing play as a series of environment interactions in the scene. The overall interaction consists of three phases: pre-interaction, involving all the actions leading up to an object manipulation; interaction, involving the ego agent directly influencing an object in the scene; and post-interaction, consisting of any downstream effects on the object. Our insight is that by segmenting play into object interactions, we can learn a latent space to model the interaction phase, which will help us learn an imitation policy. Furthermore, we provide informative goals to the policy by defining goals to be the result of an interaction. Importantly, the post-interaction period is just the same as the pre-interaction period of the next interaction. We segment play data in these phases using smooth proprioceptive signals with the environment, such as contact. Broadly, the interaction phase covers portions of time where we are directly influencing our environment. Given the segmented play data, our method PLATO first samples an object goal state, OG, from the post-interaction period. Next, we encode the interaction phase into a latent affordance Z, and then learn a policy to reconstruct the pre-interaction and interaction actions conditioned on the goal and this affordance Z. An affordance is a property of an object that defines exactly how it can be used. For example, in the block pushing task, we would say that the block affords the pushing motion. PLATO learns a latent representation of these affordances by encoding the interaction period. In order to actually learn these affordances from the interaction, we encode this trajectory tau I into latent affordance Z using the posterior network E. Here, Z refers to the pushing motion, but this learned affordance space might consist of other options like lifting. Thus, PLATO biases the latent space to focus on modeling interactions and affordances. We also learn a prior network E prime to predict the latent affordance Z from the object start state and goal state in order to regularize the posterior. This prior will be used at test time when tau I is unknown. Crucially, the prior only sees the state of the object for the start state and the goal, corresponding to O1 and OG here, when trying to predict the latent affordance Z. This prior forces the posterior to reduce its dependence on robot state information and thus helps structure the latent space to model object affordances. Furthermore, since the prior only sees the state of the object at test time, the prior will be in distribution for any initial robot position. Compared to prior methods that sample random fixed short horizon sequences from play, PLATO can capture varying or longer horizon manipulations by taking an object-centric view of play. Second, whereas prior work labels the last state in the sampled window as the goal, we more intelligently label goals by viewing play as object interactions, thus helping the prior and policy to be in distribution at test time. Finally, we no longer treat all short fixed horizon sequences as equal for task performance, as is done in prior work. As a result, the learned latent affordance space of PLATO captures more task-relevant information than would be captured through random play sequences. To evaluate our method, we consider several challenging 2D and 3D object manipulation domains. The first is this 2D block world with gravity and variations in block shapes, masses, and initial conditions. We collect unscripted and human play data and evaluate on the challenging tasks shown here. Our baselines for this and other environments are the state-of-the-art methods that sample short fixed horizon windows from play. Play GCBC, which trains a goal condition policy on those sequences, and Play LMP, which additionally learns the latent plan variable to enable a more expressive multimodal policy. Our method substantially outperforms the baselines on block pushing, pulling, lifting, tipping, and the side rotate tasks. This is true for both scripted play and human play data, and even for the much more challenging side rotate task. We run experiments in 3 challenging 3D simulation environments with complex tasks covering a range of objects and affordances. The first is block 3D platforms, shown on the left, which has pushing and lifting tasks on a block with randomized block shapes, masses, and initial conditions. The second environment, mug 3D platforms, shown in the middle, replaces the block with a mug and adds in mug pulling and rotation tasks. This mug requires quite precise handling to perform these tasks. The third environment, Playroom 3D, shown on the right, is designed for tasks involving the 3 scene objects, the cabinet, the drawer, and the block. Tasks here involve opening and closing the cabinet and drawer, pushing the object, as well as moving the object to and from the cabinet and drawer. Tasks here are especially complex and have varying horizon lengths. For block 3D platforms, PLATO substantially outperforms the baselines in both the lifting set and the pushing set. PLATO does substantially better than the baselines for lifting tasks. For the mug environment, PLATO outperforms the baselines in lifting, mug rotation, and pushing tasks. PLATO is the only method to do well on all of the tasks, emphasizing our method's ability to capture and exploit a wide range of affordances. In the playroom, PLATO does substantially better than the baselines in object pushing tasks, cabinet manipulation, drawer manipulation, and moving to drawer and cabinet tasks. PLATO is especially adept at the open and close tasks for the cabinet and the drawer in comparison to prior work. It also outperforms on block manipulation tasks like pushing and moving to either the cabinet or drawer. Notably, the baselines are unable to perform well on cabinet closing due to the longer horizon of this task, but PLATO achieves high success. This demonstrates PLATO's ability to scale to complex and varying horizon tasks. We additionally deploy PLATO and Play LMP on a real robot trained only in simulation using pushing tasks. Rollouts for PLATO in the real world are shown on the right. We see that PLATO can generalize well to the real world without any real-world play, despite the gap between simulated and real object dynamics. The results across all 3D environments show that by learning affordances and linking these to long-term environment goals, PLATO performs substantially better across a diverse range of tasks. In summary, we introduce an object-centric paradigm for learning from play, which views play as sequential but unlabeled interactions with the environment. PLATO automatically extracts interactions from play using proprioceptive cues, and then learns affordances from the interaction period in order to inform the policy. As a result, our method substantially outperforms the baselines in learning from play for a variety of complex 2D and 3D manipulation tasks, including real-world pushing tasks. Thank you.